skateboard. Like, it seems like something someone would miss, but someone left the skateboard when they came off his up. Anyone. In the conference.
Okay, let's get started. Here we go. Let's get started. Okay, let's get started. Everyone needs to set a good example. Okay, here we go. So, what I've got here is an accumulation function. An accumulation function, similar to the ones we were looking at Friday. And we're going to put rate of change on the left graph. So accumulation on the right, rate of change on the left. Okay, and so I want you to recall back toward the beginning of the semester. So I'm going to pause. Look at that. That was what I wanted, 0.55. Amazing. Okay, so I'm going to pause x here. The current value of x is 0.55. Yes, I am. And, question? Okay, and so recall back to the beginning of the semester, we said if this is an accumulation function, how could we get a really good estimate of the rate of change at this moment? So now everyone think about it. How could we get a really good estimate for the rate of change at this moment when x is 0.55? Everybody think about it. We did this long time ago. Long time ago. Okay, and so
zoom in all the way in.
Zoom all the way in, and then what?
And then you can take the
Okay, he wants to zoom in on that point on the graph.
linear.
Okay, so I have zoomed in sufficient enough so that the graph, the points are essentially linear, right? So now I'm looking at a small enough interval around x. So I have essentially a constant rate of change, right? And that constant rate of change will be the rate of change at the moment, 0.55. So let's find it, ready? So I'm going to, how do I find it? So now how do I find this constant rate of change at 0.55? Do you remember doing this about a month, 5 weeks ago? Yeah, we did this. Okay, so how will I find this rate of change? Somebody knew. Yeah. Okay. That's right. So I'm going to do 0.545. Write this down. 0.67. Is that 81? Point 678. Let's just do 0.8, okay, just to make sure. Okay? So 0.545 and 0.67808. And then I'll do 0.555. Point 71609.
should be 0.555.
Thank you. Have I written these down correctly? I believe I have. Go. Find the rate of change at the moment, x equals 0.55. Find the rate of change at the moment, x equals 0.55. Okay. I got 3.801. Is that what you got? Thumbs up over here too? This should be calculating a constant rate of change should be like falling out of bed, right? You got the change in y or the change in x. Meaning really easy, right? Okay. So how can we then any questions on that? I'm gonna zoom back out. So then how does that give us any information about the rate of change graph? What can we do now in the rate of change graph given what we just calculated? Yes, sir.
It gives us a point on the
Tell me the point. What point?
at
0.55.
0.55.
Okay, so I'm going to go ahead and do that, just by that point. So when x equals 0.55, why? Because our independent variable is the same on both graphs, right? So it's still 0.55. And what does the y value on that graph over there tell us? The rate of change of our accumulation, shown on the right, at whatever x value you have. So and what was it again? 3.801? Okay. We got a point. Are we thinking of this as exact rate of change? This value, this y value, as an exact rate of change or an approximate? Okay, you want to zoom in further? We're thinking of it as what? How are we thinking of it? 1, 2, 3, 4, 5. Do we need to zoom in closer? I'll zoom in. So, what are we going to get if now I've zoomed in 3 more times? What am I going to get if I take 2 points? Okay, yeah, but our moment was how wide? 0.01. Okay, so yeah, it's still exact or still approximate. That's true, but it's essentially the rate of change at the moment. It's essentially exact. Okay, it is not. It's super close, right? It's really close. Why? Because we essentially have a linear. We have a small enough moment that we have a linear piece of the accumulation graph. Okay, so yes, it is approximate, but we're thinking of that as exact. Is it fair? Would you buy that? Okay, so then we'll put that on hold for a second, and then what was approach 2 on Friday? And you've been reading about it. Approach 2 in terms of finding rate of change from accumulation. What was that about? We did approach 1 was like an exact reversal of what we did the last month. Exact reversal. And then we said we're going to do a new approach. And who can describe the new approach of starting with accumulation and our goal of finding the rate of change? Somebody new. What was that about, that new approach of doing this? Yes, sir? Okay, right, so other way around, Right, so the interval traveled with x. Rather than starting by defining intervals, so we're going to do intervals, right? We're going to plot intervals, and we're going to let x increase through the interval, so let's just show this. Old way, right? Old way. Intervals are already set, and then x travels through these intervals that are already set. New way. Oh, that's unfortunate. New way. Let the interval travel with the current value of x. So it's continuous, right? So we get this continuous, for any value of x, we get some different rate of change associated with that value of x, rather than the rate of change being the same in every predetermined interval. Okay, so let's go to our point that we're interested in. 0.55. The current value of x is 0.55. And right now, h is 0.4. So I want you to find the rate of change with this. So x is 0.55. And h is 0.4. Find the associated rate. Okay, same current value of x, 0.55 that we did. But now this h is 0.4, and so it's based on an interval of 0.44 starting at 0.55. Or sorry, h is 0.4, starting at 0.55, find the rate of change associated with that. Go. Oh, you can't really do that, can you? So what do you need? You need some information. At 0.555, it's 0.6. Can you read that on the screen? It looks like all 9s, 6s, and 0s to me. They're all mixed up. 69691. 0.69691. Okay? And this point is 3.5914. 3.5914 is the y value. $6966, is that what we said? 6969. I got 7.236. You got that? Did you get that? 7.236. So this approach two of finding the, all right, so, okay, let's graph. So what piece of information did we get then? What piece of information did we get over there? That at 0.55 we got a rate of change of what? 7.2362? 3? Oh, let's just make it blue. Blue to match the blue. Okay, so this new way, this new approach of finding the rate of change gives us this continuous stream of rates, right? Because as soon as x changes a little bit, that rate will change according to the new interval starting at x. This new approach, does it give approximate or exact values of rate of change? Approximate or exact? With h equals 0.4, good approximation or not so good? Not so good. Look, we're assuming this is really, really close to the exact. We calculated just by zooming in and getting a linear piece of the graph. And then here's what this is doing for h equals 0.4. Okay, so let's take a look at, if we were to do this then for every current value of x, if we were to do what we just did for every current value of x, this is what we would get. If we did it for every value of x, this is the graph that we would get. Okay? But what we want is the exact rate of change function. So even though this is continuously giving us changing rate of change, it's approximate. So, and we can see clearly at 0.55, it's way off, right? It's way off. And so here's what the exact rate of change function looks like. There's the exact rate of change function. Okay, but we have the tool to get the exact rate of change function. What will it take in approach number 2? With approach number 2, what will it take to get the exact rate of change function? Smaller h, right? Smaller h. So I could choose h to be, here's h of 0.26. It's better, right? It's better. Every time I make h smaller, my approximate rate of change function does a better job being the exact rate of change function. So here is h 0.005. When h is 0.005, we essentially have it. We essentially have it. Okay, and then we saw last time so for any current value of x now, for any current value of x, what is the coordinates of this point right here? What are the coordinates of that point for any current value of x and any value of h? X, f of x. Why? The left-hand side of our roving interval is always the current value of x. Right-hand side, x value. It's h further over. It's h more further over. X plus h and the function at that value of input, or the independent variable. Okay, and so what's the rate of change? Do the same thing we've just done twice with numbers, but now you have expressions. There's no difference. What is the rate of change? Right? Right, it's the change in dependent variable over the change in independent. Right there, that's what it is. And so, is that right there, that expression, does that give exact or approximate rate of change? Say it louder. It depends on h. Right now, is it giving approximate or exact? Definitely giving approximate. H is very large here, 0.4. But if h is small enough, that same expression, no difference, just smaller h, gives the exact rate of change. So it's both. It can give both exact and approximate depending on h. It depends on h. Here h is 0.005. And from our view, it seems indistinguishable from the true rate of change function. Okay, questions on that? So do you see, for a large h, you can see now that this roving, the second method that we've got is still giving an approximate rate. Okay, anybody have a question? All right, so it turns out that this function f that I'm graphing for you here is the volume of a sphere, where the independent quantity here is the radius. So if this is radius here, okay, and f of r, f of r is the volume of a sphere with radius r. So that red curve over there, that's what we want. Now I've got, and so what is that? What is that formula? Who remembers what that formula is? Pi r squared 2 pi r 4/3 pi r cubed. 4/3 pi r cubed is the volume. So this is the accumulation graph. 4/3 pi r cubed is our accumulation graph. And that red curve over there, that's what we want. So what is the rate of change of volume of a sphere with respect to its radius? Okay, well we have the first step in getting that, right? So we have our rate of change function, f of x plus h minus f of x over h. That's the key to figuring out what this function is that gives us the rate of change of volume with respect to radius. Okay, so let's explore that a little bit. Okay, so if our rate of change of f is f of x plus h minus f of x over h, right? Change in y or change in x for any current value of x and any value of h. What is that if f of r is 4/3 pi r cubed? What is that thing over there given that our function f of r is 4/3 pi r cubed? Well, what does that function say? What does that function say, or what does it do? Okay, so what does it tell you to do with the input? What does that function tell you to do with the input? Somebody new. Somebody new, yeah. Nope. What does that function tell you to do with its input? Yes, sir?
Cube the radius multiplied by times multiplied by 4/3.
Take the input and do what first? Cube it. And then take that result and multiply it by 4/3 pi. The rule of f says cube the input and then multiply the result by 4/3 pi. Would you buy it? Someone wake him up. Shake him. Time to get up. Calculus. Sit up in your chair. Sit up in your chair. Okay, don't be next. Don't be next. Okay, the rule says cube the input, multiply the result by 4/3 pi. So what are we going to do? So in this definition of the rate of change, our rate of change function, look, we've got f of x plus h. So we want to apply what the function f, what the rule tells us to do. The rule, what did we say it does? Tells us to do? Cube what? All right, which is? X plus h. Cube the input. And then do what? Multiply by 4/3 pi. That's what f of x plus h is. Just follow the rule. Take the input, cube it, multiply the result by 4/3 pi. All right? We do it again. So what's the new input here? The input is x. So what does the rule say to do? Cube the input and multiply by 4/3 pi. Those are those two individual pieces of this. F of x plus h, we just follow the rule. F of x, we follow the rule. And so then the rate of change function is what? The difference of those, then what? All over h. Do you follow what we did? Does it make sense? Anybody have a question? What am I doing? I'm applying the rule for a particular function f to the rate function and rewriting the rate function in terms of the rule of our particular function, which is 4/3 pi r cubed. So that's what the rate function is for that particular accumulation function. All right, and what does it give? It gives the value of the rate of change at the current value of x for some interval with h. Is it approximate or exact rate of change? Depends on h. Depends on h. Depends on h. Could be either. Could be either. Okay? So now we got work to do. Algebra. Some of you have been waiting all semester to do some algebra. Here's our chance, right? But sadly, we're going to let GC do it. But he could do it. All right, can you read that, or do I need to make it bigger? Is that what we just came up with for the rate of change function? I'll make it a little bigger. There it is. Okay. So what I'll do is, I'm going to copy and paste what we did last into the new line. Okay, so first we need to multiply this out. So just highlight the x plus h quantity cube. Highlight that. You go to math. And expand. That's cool. Okay. That's okay. What we were doing with the graphs, setting up accumulation and rate functions, making h small and seeing the real exact functions emerge, that's cool. This is okay. This is okay. All right. Okay, here. So now I'm going to take that, copy, paste. All right, now I'm going to highlight the 4/3 pi, okay? And then I'm going to see the hand pops up. I'm going to take it and I'm going to just move it inside. And it should have multiplied by all, there we go. So move it inside, it just distributed the 4/3 pi to all those terms inside the parentheses. All right? Isn't this fun? Okay, and now, what do you see in the numerator? What do you see in the numerator? What could be done next in the numerator? Does anyone notice? Look, I got a 4/3 pi x cubed, and over here, negative. So those become 0. So I could highlight that whole thing, and I could do math, simplify. Oh my God. And it subtracted off the positive and the negative ones. Okay? And what we notice now is there's an h in every term in the numerator, and we got an h in the denominator. So we need to what? Factor out h. So look, I can highlight h here. The hand pops up, and I'm just going to pull it left until it comes out. Just factored out h. And then I can select the whole thing. What's it going to become? Simplify. And the h over h becomes 1, and we get to this, which we can't go any further. So let's screenshot that. And go back to this. So what is that if f of r equals that? It's this. Okay? So what is this thing doing? What does it mean? Tell the person next to you. So this right here, this expression calculates what? It computes what? Explain the value that it computes. Go. Tell the person next to you. Okay, somebody new. What does this compute? Who is not? Yes, sir. The rate of change. Does it compute the rate of change at the current value of x for an interval width of h? So why? Because it's equal to this. We just did the math. We just did the algebra for this function. We simplified this. Okay, so this is still. Okay, approximate or exact? Okay, so let's say h is relatively large. That's approximate. So how do we get the exact rate function? So we're going to use this symbol to mean essentially equal to, right? Because h can't be 0. If h is 0, it doesn't work. We need a little change, a little momentary change of h for this to work. But we're saying this. Let's say let h essentially be 0. Let h essentially be 0. No, it's just a representative symbol. It's not a it's not a calculational symbol, right? It's just it represents something. Okay. So then, what is our rate of change? So what happens here if h is essentially 0? Super, super small. 0. What about this? And what about this? What happens to this when h becomes super, super small? It doesn't care what h does. It's not dependent on h. It doesn't care. So therefore, our rate of change function is 4 pi x squared. Okay, so we've achieved our goal, right? So let's go back to the graph. We go back to the graph. Okay, I trust your conversations are about the math. Just whisper. Just whisper. Just whisper. Just whisper. Just whisper. Okay, so what did we do? We made h really, really small, and we got a simple formula, right? We got a simple formula for the rate of change function. What did we get? 4 pi x squared. We got 4 pi x squared to be the exact rate of change function. The exact rate of change function for the volume of a sphere with radius x. With radius x. Okay? We talked a little bit about this before. This is called, this type of rule, simple formulas that you're used to being your whole math career, closed form. A closed form representation of the function, meaning you can just plug in, you can rapid fire, you can plug in inputs and it rapid fire gives you the outputs. As opposed to a rule that requires a process, a thought process. Closed form is rapid fire results, like a polynomial or a trig function or an exponential function or a log function. All these basic formulas you've been dealing with your whole math career. That's what we mean by closed form. Okay, so we'll talk about open form when we get back to it. Was there a question? Yeah. So open form is going to be an expression that reflects process. Okay, whisper, okay? Whisper if you're talking about math. If you're not talking about math, you shouldn't be talking, okay? Open form reflects process. We've seen an example of an open form representation of a function. What was it? Does anyone know? Okay, hold that thought. Okay, so now, without GC, f is the area of a square with side length x. What is f's rate of change function? No GC this time, okay? What's the rate of change function?
2x.
What? 2x. What's that? What is our standard rate of change function for an accumulation function f? F of x plus h minus over. What does the new function f tell us to do with the input? Okay, so here's f of x plus h. According to the rule for f, what is that going to be? X squared plus h, right? No. Take the input and square it. What's the input? And square it. That's what the rule of f tells us to do. This is a very simple rule. It just says take the input and square it. So we get to f of x plus h. We take the input, x plus h, and square it. All right, f of x. So what is this going to do for us? If we can simplify this algebraically, let h be really, really small, we can get a closed form for the rate of change of the area of a square with respect to side length. Fast. You should all know this. Middle term, not x squared plus h squared. Right? There's a middle term. FOIL. What happens? X squares go away. X squared minus x squared, leaving? 2x xh plus h squared. If we want to get a closed form, the goal is we've got to get this h out of the denominator because we want to make h essentially 0, super, super small. The problem is we can't because can't divide by essentially 0. Okay? So you can't cancel it out until you have it multiplied. You got to factor out h. So h times? So what is this? This is the rate of change of the area of a square with side length x, if your interval width is h. So how can we get exact rate of change? If h is essentially 0, then our rate of change is 2x. Okay, so my intention was for you to work through that here, but I want to get to some stuff, so I worked through it. But anybody have a question with what we just did? So for most students, this, yeah. Thank you very much. No, that's definitely still closed form. Closed form is any basic formula that would just give you rapid results. So that's not open form. Okay, that's a closed form also. Okay. My experience is that students have the most trouble with this first step. Okay? We're rewriting the rate of change function given a particular accumulation function according to its rule. And this time, the rule was square the input. So then we're going to come over here, we're going to square the input, and we're going to square the input and subtract over h. That's our rate of change. That's how we get started finding the rate of change. Okay, so what are we working on? We're working on accumulation to rate. But something just profound happened that you didn't even notice. Watch. We just learned that if f of x equals x squared, the rate of change of f is 2x. So how else could f be expressed then? If the rate of change of f is 2x, how else could f be expressed? Who's learned something in the course? Yes? Integral of? Okay, almost remember the symbol thing, remember? She got it. She got it. If the rate of change is 2x, then we can express its accumulation as the integral from 0 to x, 2t dt. Remember that? Okay, this is an example of an open form expression. Why? Because this is reflecting process. You can't plug in x and rapid fire get out values without some kind of computing like GC to do that for us. We needed GC to calculate these for us, right? We couldn't just, type in, for integral and get an answer, right? So GC had to do this for us because this is really reflecting process rather than reflecting just a basic, easy formula. Okay? Side note. Okay, so this means we've learned something else. So by learning that the rate of change of f is 2x when the accumulation is x squared, what happened? We just learned something else. We learned that this open form accumulation function can be written as what? What is that open form accumulation function can be written as in closed form as what function? X squared. So when we were creating accumulation functions from rates, we stopped at the open form. We were able to get the exact accumulation function, but that was only open form. We never got closed form. All right? Now that we've taken the reverse direction, every time now you get a rate of change function from an accumulation function, you learn two things. You learn what that rate of change function is for the given accumulation function, but you also learn now a closed form for an accumulation function. A closed form for an accumulation function written as an integral. So because that's the accumulation at that given rate, we just got, we know that the closed form of that accumulation function is x squared. Make sense? All right, you try. Okay? So earlier we learned that the rate of change function for v of x equals 4/3 pi x cubed is 4 pi x squared. All right? So we figured out that the rate of change for this volume function is 4 pi x squared. What else did we learn as a result? See if you can write it down. What else did we also learn as a result of learning that this was the rate of change function for this volume function? Can you write it out? Okay. Anybody think they got it? Somebody new? Any ladies? I haven't heard from any ladies today. Oh yeah, she did. But still, the men are beating you guys. I want to hear from a lady. Who thinks they got it? Don't be shy. Did you get it? Okay, let's give it a shot. So the integral from 0 to x of 4 pi t squared dt. What about that? Equal to? Equals 4/3 pi x cubed. We learned that if you had this open form integral, 4 pi t squared, we learned how we could write it in closed form. How can we write it in closed form? 4/3 pi x cubed. 4/3 pi x cubed. So before, when we were creating accumulation functions from rate functions, we stopped here. We said this is the accumulation function for some quantity changing at this rate. But we never had a closed form for that. Well, now we just, by doing that problem earlier, we just found the closed form for that. It's 4/3 pi x cubed. So we made a circle, right? So we've come full circle. So by being able to get a closed form rate of change function from an accumulation function, we learned that, but then we also in doing that got a closed form accumulation function from a rate function. Okay, I will add to the homework post I started on Friday, and you'll turn it all in on Wednesday.
Given how everything has progressed, I take it the phrase "power rules" will not be something we hear in this class.
No, that's what the whole mastery is about. All those rules. We're gonna do all the rules. Those are coming up like next week.
Okay.
We're starting at the end of this.
Did we do any math to go from where to there, or we just copy it? Go from where to where? To go from the integral here to the closed form here, in my eyes, we're just copying it from the volume function.
Well,
Are we doing any math to go from there to there?
no. Okay, so we did the math when we started with this accumulation function.
Right.
We were able in class today to provide with this rate of change function.
Right. Track on that.
Okay, so So we learned that. We learned that this accumulation function. The accumulation function is that.
Right. My question
So
is.
then, what that means is that we've learned a second thing. We learned a second thing. If we had an open form accumulation function, well, that has to be this. It has to be this accumulation function.
I guess my question is, if you were given an integral without me giving this here, and you
No,
turned
so
it
the
into
reason
this,
that we knew that
because we were given the accumulation
because we found the rate of change function. Starting with the accumulation function, we were able to find its rate of change function. Because of that, we also learned that this open form accumulation function equals that.
Okay.
Does that help?
Yeah, but I guess my question is, does this work for any open form? You can go to here, or is it because?
At this point, it would only be the ones for which we found the closed form rate from the accumulation.
Okay. All right.
So I can't just change this right now to say 4 pi square root of t. Well, so that would be the accumulation function, but we wouldn't know what is a closed form for it because we never derived, we never found that as the rate of change function of something. That's the only reason I'm able to do this is because we found the rate of change function starting with that accumulation function. So because we did that, now we've learned that also this open form accumulation function has this plus 1.
Okay.
Yeah, so it's only so we can only do these two right now because we did that one and we did this one. So these are the only two we can do. Does that make sense?
Yeah.
In terms of rewriting it this way.
Yeah.
Okay. That's actually what my